Hello guys, welcome back once again to my channel Digamma. It's been quite the long time. I was quite busy with my work again as usual, and I just didn't have any time. But now I'm back with a few more integrals. And with that being said, as usual, let's get started. So, first of all, the integral in question is now a double integral for this video. So we have integral I to be the integral from 0 to 1 of square root x plus square root y all divided by 1 minus xy square root of the square root of xy. So that's a nested radical right there. Dx dy. Before we do anything, let's simplify this, and simplification is possible for this because there's a nested radical and we don't really like nested radicals in mathematics. It's always best to convert such kinds of monstrosities into powers, and in this case it's going to be a negative fractional power. So we have integral 0 to 1, 0 to 1 as it is, and then we have the numerator, which is square root x plus square root y, and we have the term in the denominator, which is not the nested radical, which is 1 minus xy. Fair enough. But the nested radical is a square, is a square root, my bad, of a square root, which is power 1/2 in the denominator, which becomes in the numerator power negative 1/4. Dx dy. Now, a further simplification is possible. Notice the denominator, we have 1 over 1 minus xy. And when you see something that has 1 minus xy in the denominator, the infinite series, the infinite geometric series should cross your mind. So, the infinite geometric series formula and again I will talk about the applicability of this formula in terms of the radius of convergence. So we have 0 to 1 is what the x and y are, and all we need for the radius of convergence condition for the infinite geometric series is the quantity that was along the 1. So in this case it's the xy to be less than 1, which is basically true. Actually, we can even include 1 from the range of integration, because otherwise the denominator will blow up. And that's fine, we need a strict inequality for the radius of convergence. Cannot have those problems with the the boundaries. With that, we can just convert all of this, can rewrite it, and maybe I should also use a different color here. Yeah. Integral 0 to 1, integral 0 to 1. The term in the denominator produced an infinite series. So sum n equals 0 to infinity square root x plus square root y times x y to the minus 1/4 from before. And we're going to have a power n because that was the infinite geometric series that we're going to get from the term in the denominator. So that's r to the n. R in this case is xy. So we have xy to the n, and we can add the powers. So dx dy. If this isn't clear, what just happened is we had 1 over 1 minus xy. This, from the formula of the infinite geometric series, became sum from n equals 0 to infinity of xy to the n. And that's in the numerator. So that term here, and this original term in the numerator from the nested radicals, which was minus 1/4 power, you can add those powers up using the properties of exponents. So you get minus 1/4 plus n. And now simplification should be a lot easier. Before simplification, let's interchange the sum and integrals. And again, you can justify this using dominated convergence, all sorts of theorems. But also remember this integration interval, 0 to 1, 0 to 1, is a unit square. It's a compact interval. It's a compact region of integration. So it should be quite easy for us to justify that we can do this if one wanted to be absolutely rigorous. Okay, so now we can separate this into two terms. So the first term will be associated with this square root x. The square root x is x to the 1/2 power times x to the minus 1/4 plus n. I'm just expanding the xy to the minus 1/4 plus n as each individual term. Similarly, we have thing on the y. And then we add that to the square root y term. So we have the x to the n minus 1/4, and we have the y to the 1/2 from the square root y, and then y to the n minus 1/4, just like the x, and dx, dy. I think everything up till now has just been simplification. We haven't really integrated anything. So now let's actually do that. So again, change of color. So let's integrate with respect to x. You could also integrate with respect to y. But maybe let's simplify the powers further. So everything else around it is always the same. So 0 to 1, 0 to 1, we have 1/2 x to the 1/2 times x to the minus 1/2. So that's x to the 1/2 minus 1/4, which is x to the 1/4. So 1/4 plus n, so n plus 1/4 times y to the n minus 1/4, plus similarly with the y. So x is the same, nothing on the x, and then we have y to the n plus 1/4. So there's some sort of symmetry. You might notice that just by looking at the form of the this integrand. But let's choose a different color. So I is sum from n equals 0 to infinity of 0 to 1, and we're integrating with respect to x. Could be y again from the symmetry and this integral that does not really depend on there's no nested integrals here, so interchanging the order is completely fine. So when we do that, integrate with respect to x, we get y to the n minus 1/4, which is unaffected, divided by the power on the x plus 1. So that's n plus 1/4 plus 1, which is 5/4, and x to the n plus 5/4. You add 1 to the power. This is the product, the power rule, sorry, of definite integrals. Plus y to the n plus 1/4 divided by, now add 1 to the x power, so that's minus 1/4 plus 1 is 3/4, n plus 3/4, and we have x n plus 3/4. Let's give ourselves some space. Dx dy, that's a dy. Okay, and now we still have to plug in. There's no dx. We integrated over x, so that's dy, and the limits of integration are from x equals 0 to x equals 1. Now at x equals 0, both the terms vanish, but at x equals 1, that x term is just 1, so we can simplify. And 1 raised to any power, even if it is an integer power, is 1. So we get y to the n minus 1/4 divided by n plus 5/4 plus y to the n plus 1/4 divided by n plus 3/4. That's the integrand dy. Okay, and since there's only one integral, just integrate with respect to y. And these are pretty simple to do. It's just the power rule of integrals. In this case, it's a single variable integral, so that's absolutely fine. We don't need that integral. We're doing it right now. So we have y to the n minus 1/4 divided by, actually we should have 1/4 minus 1/4 plus 1, which is 3/4, n plus 5/4 times n plus 3/4 and y, the n plus 5/4 divided by n plus 5/4 times n plus 3/4 evaluated 0 and 1. And again, similar to the x, we just care about the value at 1. At 0, it all vanishes. And this is basically the same term in the denominator. So we get 1 over this product in the denominator and 1 over the same product in the denominator. So we have 2 times that one term, which is 1 over the crazy product in the denominator. So n plus 5/4, n plus 3/4. Okay, fair enough. Now, what do we do? Well, whenever you have a product of linear factors like this, for integration and also for evaluating these sums, it's best to use partial fraction decomposition. So I'm going to decompose after choosing a different color. I'm going to decompose 1 over n plus 5/4 times n plus 3/4 to be a, which is some constant, over n plus 5/4 plus b over the second factor, which is n plus 3/4. Cross multiplying and eliminating the denominator, 1 equals a times n plus 3/4 plus b times n plus 5/4. Group the terms with order n, so n, the coefficient of n is a plus b, and then the rest is the constant term, which is 3a plus 5b all divided by 4, and that's equal to 1. So now compare the powers of n. So there's no n power. The power of n on the left hand side is 0. So the term which has the coefficient of n on the right side should be 0. So a plus b is 0. Meanwhile, the constant should be 1. So 3a plus 5b over 4 is 1. This gives us b is just minus a. This equation gives us 3a plus 5b equals 4. Let's plug in b equals minus a into the second equation. We're solving two equations simultaneously. Now that gives us 3a 5a is 4. So a is -2 and b has to be +2. Okay, perfect. We know the coefficients. We can split our infinite sum the way we want after choosing yet another color. So I, which was now this infinite sum, it's 2 times sum. You have two sums from 0 to infinity of a over n plus 5 by 4. It's minus 2 over n plus 5 by 4. And b, which is 2 over n plus 3 by 4. I should have probably bracketed this better. So I need another bracket here for the sum. Okay, I can pull the 2 out. I can really pull the 2 out. From everywhere, I get a 4. Sum from 0 to infinity. 1 over n plus 3 by 4 minus 1 over n plus 5 by 4. And this should actually remind you of the videos we've made in the past. This is actually the form we can of the digamma function. Not just one, but a difference of them. So digamma of z was negative Euler-Mascheroni plus sum n equals 0 to infinity. 1 over n plus 1 minus 1 over n plus z. Now what happens when I take a difference of them? So digamma of a minus digamma of b. Well, the Euler-Mascheroni, which is a constant in both the cases, cancels. And the 1 over n plus 1, the constant term, also vanishes. We have 1 over n plus b minus 1 over n plus a. So the order is reversed. So a was first on the left side, it's last on the right side. Remember that, because we can exactly use this formula to estimate what the quantity here is, this sum here is. So using this nice formula we get 4 times sum. Well, we don't need the sum anymore. We have digamma 5 over 4 minus the digamma of 3 over 4. And there is yet another identity that will be useful for us here. That identity is the recursion formula for the digamma, which is digamma of x plus 1 is just digamma of x plus 1 over x. So that gives us I to be 4 times, and we're gonna use that for the 5 over 4. X is 5 over 4, or rather 1 over 4, because 1 over 4 plus 1 is 5 over 4. So that's digamma of 1 over 4, which is this first term, plus 1 over 1 over 4 minus digamma of 3 over 4, which we can write as 1 minus 1 over 4, and you will see why. So this gives us 4 times 1 over 1 over 4 minus, and now for this term, digamma of 1 over 4 minus digamma of 1 minus 1 over 4, we use the digamma reflection formula, which is digamma of 1 minus x minus digamma of x is pi times the cotangent of pi x. When we do that, we get a minus sign from reversing, because we need the 1 minus 1 over 1 minus 1 over 4 to be the first term, but we have to flip them around, so we get a minus, and we multiply it by 4. So 4 pi cotangent of x is 1 over 4, so pi over 4. Finally, I is just 4 times 4 minus 4 pi, because cotangent of pi over 4 is 1, which is 4 times 4 minus pi, or 16 minus 4 pi. And that's the answer to this integral. Let me write it once again for the sake of posterity. Integral 0 to 1, 0 to 1, square root x plus square root y, all divided by 1 minus xy, square root xy, dx dy was a double integral, 4 times 4 minus pi. That's it. We've solved it. Well done. Thanks for watching this video, guys. So I know I was rusty in this one, clearly. Not only did I revert back to the old format, but it's also been quite a long time. Well, I'll see you in the next video. Till then, peace out, stay safe, and keep doing math. Catch you later.